Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 21st, 2025, about 3 days ago. This paper proposes an actor-free, purely value-based method that makes continuous control feasible by shaping the Q function so its best action lies at one of a small set of learned control points. The paper is titled, Actor-Free Continuous Control via Structurally Maximizable Q Functions. And as we'll see later, the implications for stability and efficiency are quite significant. In short, Q3C matches state-of-the-art actor-critic performance on standard tasks and clearly wins in constrained action spaces. Also, the authors shared the official Q3C code on GitHub. You'll find a pip installable package with the Q3C modules, Hydra configs, and training scripts like scripts/run experiment.py, plus requirements and setup. The repo walks you through Muju Co-based experiments with W and B logging and environment-specific hyperparameters, with examples for Hopper, Half-Cheetah, and Walker 2D. Alright, Figure 1 shows the wire fitting idea that underpins Q3C. The curve is built by interpolating a finite set of learned control points, each with an action and a value, using inverse distance weights. Because the construction guarantees the peak occurs at one of those points, the best action reduces to picking the highest valued control point. The smoothing term adjusts how tightly the curve passes through non-maximal points, yet the maximizer still sits on a control point, which is valuable in highly non-convex Q landscapes. So while Figure 1 showed why wire fitting guarantees a maximizer at a control point, Figure 2 presents the end-to-end Q3C architecture. The left module generates end control point actions from the state, producing diverse candidates. The middle stack evaluates each candidate with a shared Q estimator, which keeps values consistent because the same network scores all points. The right panel interpolates these scored points to form Q of S, A, and the greedy action is the highest valued control point. So, while Figure 2 outlined the pipeline, Figure 3 presents learning curves across standard environments. The panels show that Q3C closely tracks TD3 in final return and usually surpasses NAF, wire fitting, and RBFDQN, which signals that the control point design is effective. Hopper suggests rough parity with TD3, while the ant task shows a noticeable gap where TD3 leads. Shaded bands indicate variability across seeds, so the tighter orange regions reflect steadier training. So, while Figure 3 summarized learning curves, Table 1 reports final returns on classic MuJoCo tasks. The table shows near parity with TD3 overall, with Q3C around 9,500 on Half-Cheetah versus about 10,000 for TD3. Hopper lands near 3,200 for Q3C, slightly ahead of TD3. NAF, wire fitting, and RBFDQN trail by wide margins, and Ant remains the one case where TD3 leads. So, while Table 1 reported final scores on standard tasks, Figure 4 shows learning curves in restricted action spaces. The orange Q3C traces rise higher and stay steadier because structural maximization selects the best control point directly, which avoids local traps in non-convex Q landscapes. The blue TD3 and other baselines flatten or wobble, signaling policy stuck at suboptimal actions. Shaded bands indicate variability across seeds. So while Figure 4 highlighted rising curves, Table 2 reports final returns in restricted environments. Q3C leads across the board, reaching 1,000 on inverted pendulum box, about 4,360 on Half-Cheetah box, and around 1970 on Hopper box. TD3 posts roughly 780, 2,280, and 1,400, which suggests gradient-driven actors got stuck in local optima. NAF spikes on Half-Cheetah box but lags elsewhere, and plain wire fitting collapses, which underscores why the control point design and stabilizers matter. Alright, while Table 2 reported restricted environment scores, Figure 5 shows ablation learning curves that test which pieces matter. The orange full Q3C trace consistently rises highest across Hopper, Bipedal Walker, Walker 2D, and Half-Cheetah, which signals that all components together stabilize training. Removing ranking, normalization, conditional Q values, or diversification lowers returns and increases variance. The plain wire fitting baseline lags far behind, especially on Walker 2D and Half-Cheetah. Wrapping up, two takeaways stand out. Shaping the Q function with learned control points makes greedy action selection trivial and stable, and the actor-free design matches strong baselines on standard tasks while clearly winning in constrained action spaces. The broader implication is simpler: more robust continuous control for real robots and offline learning. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.